Hello and welcome to Stat 3050 at the University of Wyoming. Today we're going to be talking a little bit about linear regression. So linear regression is this really interesting tool that we can use to relate two things. So we have something on an x-axis, our predictor variable, and we have something on our y-axis that would be our outcome, and we can plot those points and draw a line through them and kind of figure out how x is affecting y. It's pretty interesting, it's pretty cool, it's a very useful tool used all over the place. And so we're going to talk a little bit about how it started. And so we've got this fella here, this fella right there. We'll give him like a little hat. Yeah, that's very appropriate for him. So that's Francis Galton. He was sort of the first person to coin the term regression. And so regression is this thing, or at least that he noticed, that as time went on, he noticed that the heights of people were getting, taller, looking at data, right, from the past up until the point that he was looking at it. And he noticed that, you had some people that were sort of far out, but it did sort of regress back towards the mean, which is this line, right, this sort of expected value. And so he was like, okay, let's see what we can do with that. And that's sort of what caused the start of regression as we know it today. And so we use it in all sorts of different fields and different studies, biology especially, but we see it in chemistry, astronomy, big time in economics. They do things a little differently, but it's all the same, right? It's all the same sort of idea. And so, well, what's the point? What are we doing with regression? That's a joke. What's the point? Because we're working with points. Thank you. So what is the point? Well, we use regression for two things. The first thing is finding a relation between two variables, usually x and y, whatever it may be. It could be height and weight. Use that example a lot. It could be mean income or income and, overall happiness or something like that, some kind of scale. But what we do, we just plot them. We look at that slope, right? We look at the slope, and that slope tells us how x is affecting y, or how y is affected by x. And when we get into multiple regression, we have multiple predictors. We're not able to plot them as easily, but it's the same kind of idea. We're looking at slopes, we're looking at that sort of stuff to make a relation between one predictor or two predictors or some number of predictors and some outcome, some y variable. Also, we use regression to predict y with a new x, right? So drawing this again, I'm going to be drawing this a lot. When we have data that looks like this, right, we're kind of able to say, okay, what if I had an x, some value x, right about here, some new variable x, or some new value x. Well, what we would do if we were doing this by pen and paper, we would have our regression equation. And what that equation essentially is doing is just drawing up and then drawing over to some y value, some new value, right, that we haven't really seen yet, and at least that's not in our data. And so that's sort of saying, like, okay, we don't know what that value is, but we're able to, predict it pretty well within some range. One small caveat, though, and let me draw this in another color. We'll do it in green here. Is sort of the rule with regression, and we'll talk about this more later, but we're sort of restricted to the data that we have. We're not really allowed to say anything about anything over here in this area or anything way off over here, just sort of against the rules, because we don't know how the data is behaving or how the data are behaving outside of the data that we have collected. So just keeping that in mind, we do have a few assumptions, just like in ANOVA and t-tests that we were working with earlier in the semester. We also have assumptions for regression too, and they're about sort of the same flavor. But we will talk more about that just here in a second. So, well, how do we visualize regression? Well, we use what's called a scatter plot. So these little dots here, one for each x and y, and then we draw a line through it. So this blank here is scatter plot. Now I am writing with my finger here, so please excuse any poor penmanship. This is me, so I'm just going to put my signature next to it. There we go. Just kidding, we will erase that so we know what's going on. But that is a scatter plot. All right, and so what is a scatter plot? Well, we have, our sort of basics here. We have some x variable, some y variable, where our x is the predictor and our y is the outcome. So we see that right here. And then we have one dot per x and y, so sort of a pair situation. And then we are able to draw this, right now, this blue line going through it. And the way that it's done, essentially, is it just minimizes the amount of distance between each sort of point here. So the math behind that, can be fairly onerous, but we do know that this is the most optimal line, minimizing the distance between it and all the points. So nothing, not too important to get hung up on, but just, interesting to know. And then the shaded area around it, this is known as our 95% confidence interval band, right? So we'll talk more about this, in another presentation. But we sort of have this band that goes around the line. It sort of tells us where the line could be if we were to get more data or if we were to look at the whole population. And so, with that being said, let me introduce this data set that we're working with. This is a real data set. About age and muscle density. And so we can already kind of see that as time goes on, sort of as you age, right? As you age, muscle density goes down, right? So that makes sense, sort of, biologically at least that makes sense. But we have ways of actually modeling it and seeing how that behaves, how these two variables behave with one another. Well, okay, so how do we do that? Well, I've sort of mentioned earlier that we have this idea of a slope, right? That sort of tells us how age is affecting, density here. And so, if you remember from algebra, way back in the day, right, we have this formula for a line, this y equals mx plus b. And essentially, we're doing the same thing in regression. Pretty cool, pretty simple, except we get a lot more meaning out of it, especially now that we're working with real data. So this is the formula for a line, mx plus b. In regression, you'll see it two ways. You'll see it swapped around to b plus mx, or you'll see it more frequently in this sort of notation, this y equals beta naught here, not or 0, and then beta 1, and there should be an x1 right there. So let me draw that just so we know. Small typo. Since we're only working with one predictor, doesn't so much matter, but to be technically correct, beta 1 x1. And so that's it, right? It's all saying the same thing, but what do they represent? What do these different variables here, these different symbols, represent? Well, great question. Just absolutely beautiful. So this first one, our y, pretty obviously, we've been talking about it now for a while. Our y is our outcome. Our y is the outcome, right? So that's the thing that we're trying to sort of predict, right? Trying to model. We're trying to see how it behaves when we incorporate, different variables into it. So that's our y. Beta naught here is our intercept. And I'm just going to, since I'm writing with my finger, intercept is, int is short for intercept. So if we were to trace this line all the way over, we would see that it intersects, it sort of intercepts the y-axis there at about 110, we'll say. And so that's really what that is representing. Our beta 1 here is the slope. So when we get into multiple regression, we'll sort of see it notated like this. It's beta k, xk. Whatever, no big deal. That's 2 k's, good lord. But no big deal, right? But this is just representing some number. So 1, it would be 1, 2, 3, 4, all the way up to some number k. So if we wanted to be even more technical, anything here that is not a 0, is some slope. We'll represent that with k. Not too important to get hung up on those details, but just so you know. All right. And then what else? Well, we have our x. And that is just going to be the predictor value. In this case, it's age, right? So we've got all that. That all looks good. Let's sort of see it kind of blown up on this figure here. What I said earlier, this is our intercept. This is where the line intercepts the x-axis. The y-axis. And then our slope, you remember it probably as rise over run. We're not going to worry too much about that because we don't have to do anything by hand, thank the Lord. But that is how it's calculated, just sort of how it is behaving with our y variable here, our outcome. And then we see everything else. We see our age is our predictor, our x, right, and then outcome, y. And that's all good. So one thing you'll notice is that there's a few points on here, and let me erase the ink so we can see it all better. You'll notice a few points on here that are like pretty close to the line. Like this one over here. This one's pretty much on the line. We see this one would be if the line was drawn all the way through, which it's not, but that's okay. That would be on the line too. But we see that there's like this one right here is really far away from the line. This one, way up here is also really far away from the line. This one especially, right? And so this value, this distance between the line and the observed value, right? So this is our observed. We can call this OBS for observed. And then whatever value corresponds to that on the line is known as our fitted value, or our estimated value. Fitted, right? Fitted or estimated. Well, if we were to take that difference between that observed and the fitted, we would get what's called a residual. And so these residuals are pretty much what tells us how good our model is. And we want these, if we could take, values for each of these residuals here, this distance here. If we were to record that, then we would get, and plot that, we would get a residual plot. And that's where we get a lot of our meaning from the model. And it kind of tells us how well our model is doing. We'll talk more about that in a little bit. But let's get into how we actually do this in R. And so I'm using the ggplot function here. ggplot is part of the ggplot2 library, or more generally, the tidyverse library. Super helpful. Makes R so much easier to use. I'll tell you what. All right. So just be sure that if you want to use it, to call it first. If you don't have it installed, you can do that install.packages and then in quotation marks, tidyverse. And so we want to be able to code this, create this, construct this in R and make it look, decent. We want to make it look okay. Well, and so how do we do that? Well, just like always, we've done in this class, we've used the ggplot sort of when we're looking at like an ice cream sundae, right? This is our, bowl. This is our bowl, right? The geom point, geom smooth, that's the ice cream, that's the ice cream. That's ice cream. We'll do 2 scoops because they're both important, right? And then the theme classic, we're going to get so fancy with it. The theme classic is just the cherry on top, right? Cool. So with that being said, We'll erase my ice cream sundae. I am going to get ice cream later today. Thank you for that. So how do we do this? Well, so we plug in our data. Let me get a more pleasing color here, more aesthetic color. So we plug in our data. I've called it muscle, right? Earlier in some other code before line 21. And then we want to plot our x, our predictor, in this case age, and we want to see how that affects density, our y. And then geom point, you can leave that blank, as far as what goes, any arguments that go in here. And then geom smooth, not geom line, it's a little bit misleading. Geom line instead just kind of connects all the dots together and it looks gross. But what we want is geom smooth with the method equals lm, and that lm just stands for linear model. LM stands for linear model. The default, if you were to leave this out, is lowest. It's a lowest curve. Looks kind of funky. Instead of doing just a straight line through it, it makes a straight line through 3 points, I believe. Makes a window and then does the next 3 and the next 3 and the next 3, and then kind of smooths out. So you'd see something more like kind of like this sort of thing. So it kind of helps sometimes, but for this class and for regression in general, this is what we want. We want this nice straight line. Well, so we've got that. We've got the plot. We know what it looks like. But what I want to know more about the equation itself. And let me write this not in algebraic terms, but let's write it in stat terms. Okay, so beta naught, we want to know what our intercept is. We want to know what the slope is, right? And then our x, always stays blank because that's where we plug in our values. Okay, so how do we do that? Well, just another great question. So we use the linear model function in R. And it's pretty simple. It's the same notation. It's the same notation as the ANOVA, where we have some formula of our y as a function of, that tilde kind of translates to as a function of, and as a function of our x variable, our predictor, age. And then we just plug in the data equals muscle, or whatever data set you're working with would go in there, and then you're set. With this, just a quick note, unlike ANOVA, where we had to turn things from a wide format to a long format, let me do like that, right, okay. So instead of doing that, we can just leave things as they are, which is very helpful, right? So you typically, in your data, the way that it's structured, let's say that you have 2 columns, looks like this. You have your one x and your one y with all the values in there. That's the way that we work with regression. That's the way that it should be as far as storage goes. So just keeping that in mind, you do not have to use any sort of data structure manipulation, which is good. Makes things a little bit faster, I think. Okay. So we've got that, and we've got our model built. We have I've called it linear model, linear_model, and it's built. But we need to figure out what exactly is going on. We need to get all those coefficients. We need to get what the regression equation looks like. We need to see what sort of p-values we're looking at. So we use the summary.lm, and then you would just put your linear model in that function. It's pretty simple. That's really all you have to do. If you're curious, you can pause the video, take a look at the details that I have here. Nothing too crazy, but just more or less if you're interested in some extra stuff that this function does, you can look at that. But we are not going to worry about it for right now because we have some other packages that can do these things a little bit better. So we've hit Control-Enter on summary.lm linear model, and we get this. Good Lord. This is a lot. It can be a little confusing, especially if this is your first time working with regression. But let's take a look at it one line at a time, because there's a lot in here that is not totally necessary, but we want to make sure that we get the right info and that we're sort of interpreting things correctly here. Okay, so what is this? Well, this is just more or less the double check to make sure that you've got everything in there correctly. If you see anything odd in here, in this area, right, maybe go in and double check and make sure that your model is built correctly, you've got the right data and the right order of things here matters. So we've got that, and that's okay. And then, well, okay, so we're working with these residuals too. So in ANOVA, the residuals looked a little different, but it's still the same story, right? It's sort of that estimated value, that fitted value, minus the actual value, right? Or some combination of that. And so what it does, depending on your data set, it sort of gives this 5-number summary of the residuals. And so just as a reminder, this is sort of what our data look like. I'm just going to draw 2 points, one here and one here. This distance between our point and fitted value on our regression line, I'll draw it in red here, just so we know. Just so we know. Cool. Close enough. Okay, so that is what's being plotted. It's this difference, okay? And so typically you want that difference to have a median to kind of be centered at around 0, which in this case it kind of is. It's maybe a little bit less centered around 0, but that's okay. So you'll see sort of some symmetry here and here, and you expect to see some symmetry here and here too. So let me I'll do this in a slightly different color so we can see, right? And so what that's saying is, well, we really just want residuals. I'm going to call residuals just resid, and I'm going to use some kind of fancy notation here. We want the residuals to be distributed normally with a mean of 0 and a standard deviation of 1. Nothing too crazy here, and we'll work more with residuals in a second. But you can kind of get an idea of how symmetric your residuals are based on this 5-number summary. And so we can kind of see that the minimum, is not as the degree that it goes is not the same. It's not the same that we see here with the max, right? So as far as absolute value goes, the max is a larger number than the minimum. But that's okay. We'll talk more about that in a little bit. So then the bulk of it. So when in regression, we have this y equals beta naught plus beta 1, x, and 1. And then we call these values here, these beta values, we call them coefficients. And so this is our coefficient for our intercept, and this is our coefficient for our age. And it just so happens that it's these values here. So if we wanted to, and in the next slide we will, we could take those values and plug them in for beta naught and beta 1 and be totally fine. And that would be our regression equation. Pretty cool. So what do we have? Well, so we have the estimates for the coefficients. So that's good. We have our standard error for these estimates of the coefficients for these. So that's cool. So that's just sort of saying like, okay, what's the over-under, more or less? What's the over-under for the estimate here? It's looking at some sampling distribution of the coefficient, blah, 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 blah. We don't need so much to worry about that for this class. You will in other stat classes, but for right now, let's just not worry about it. And then recall that our t-value and our p-value both essentially tell you the same thing. So let's see. We have, let me draw it like this. I'm just doing some recall. We have some number line, right? And we have our distributions. Looks something like this, right? We know that as these peaks here go further apart, this p-value, this area underneath becomes smaller, right? So that's okay. That's essentially what it's doing here too. We're just looking at, more or less the distribution of the coefficients rather than the distribution of two samples. Again, the math, don't worry about it. But we see here, our p-values are both under our alpha. So p is less than alpha, and our alpha equals 0.05 for right now. And pretty much always will. We're not going to worry too much about changing that. That's just more or less, that's just the convention. And that's okay. That is okay. And so we see, let me fill in this blank here. This t value is the number of standard error units. Standard error units. Good Lord. That the coefficient is away from 0. A little difficult to interpret that with the intercept, but the age makes sense, right? The age makes sense. So right now, our age slope is negative, looks something like that. But if that p-value, and we'll talk more about this in a little bit, but if that p-value were greater than 0.05, then we know that that slope probably is not this. It probably is not this, and it might be 0, which looks just like a flat line, right? And so that would say, well, there actually is no relationship between x and y. You know, x is not doing a very good job of explaining y. But we'll talk more about that in just a little bit. And then we get these little symbols over here representing the p-values. Again, in this case, they're both way under 0.05. But sometimes these symbols can be a little misleading. They sort of do some rounding stuff. More or less, it's just so it catches your eye and not so much for you to base your interpretation on. So just keeping that in mind. Okay. Well, so what is our regression formula? Well, pause the video and just take a second and tell me what you think it is. Well, don't tell me because, I'm not here right now. But just try writing down, based on the stuff that we see up here, what our regression equation would be. Okay, so I have assumed that you paused the video. Good for you. You probably got it right. So let's check it out. I'm going to do some rounding here, just because. But we have 156, and then 0.35 is our intercept, so that's good. And then minus 1.19. We don't need to round any further than that. So that's good, right? That is okay. And that is our regression equation. Pretty simple, right? Pretty cool. And so our interpretation with this, this is a very important thing. This is very important. So keeping this in mind, we see that with this linear model, we have, for every 1 unit increase in x, for every 1 unit increase in this value, y changes by this value, by 1.19, by negative 1.19. Don't forget the negative, very important, right? So as age increases by, 1 year, we'll say, muscle density decreases by this much, by negative 1.19, or changes by negative 1.19, decreases by 1.19, increases by negative 1.19, all saying the same thing. Some of them are easier to understand, so just keeping that in mind, because you're telling a story here with regression. So that's typically how the interpretation works. Pretty simple, pretty okay. And I did just erase everything totally on accident, but we'll just write it back here. Fast forward if you don't want to see me do this. And then negative 1.19. Very cool. All right, so we're good. We're set. And then we have one last part of the model that we're looking at. Not too important to get hung up on, except for this line here, the second line here, where we have multiple R-squared and adjusted R-squared. And so that's okay. The two different things, right? Telling you the same information, but one of them is doing a slightly better job. And so we won't so much worry about the standard error of the residuals, and the degrees of freedom, f-stat, whatever, more or less for a more advanced regression class. But one thing, since we're only working with one predictor and one outcome, right? This multiple R-squared is really just the R-squared. By default, R just says it's multiple because it's easier to print. But just keeping that in mind. And we see here that the R-squared is 0.7501, and the adjusted R-squared is 0.7458. Well, what's happening there? Well, it turns out that with the multiple R-squared, it does a pretty okay job when you have a decent sample size with, not a whole ton of additional X, variables, additional predictors. But it's oftentimes very, very sensitive to increases in the number of predictors that you have. So R-squared always goes up, when you add another variable. Always, 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 always. But what this adjusted R-squared does, all it does is just account for that. And then also sample size too, right? So if you have a really small sample size, these two values will be different. And the same thing with the number of predictors. So we'll talk more about that when we get into multiple regression. I have a whole PowerPoint on R-squared. It's very important that we sort of know what exactly is going on. But for right now, this is just the intro. Okay, so the model is built, and we have our regression equation, but can we trust it? Well, you're just asking really good questions, and for right now, I'm going to stop the video so we can talk more about trusting models and making sure that they are accurate and all good. All right, I'll see you soon.